Okay. Okay. Now, we finished nearly. What time is Andy on? Oh, yes. We finished, where's Donna? No? Okay. We finished recently the materials section, except for one lesson, which I think I'll do later. So the materials is practically finished. There's only one lesson left on materials, which is to do with resistivity and resistance of materials, electrical resistance, okay? So I'll do that later, but the materials is finished really, except for one lesson. Anyways, we're going to go on to the next part of the course. So we have now 4 parts completed: mechanics, electricity, waves, and materials. So now we're on fields. Some of this will be a bit of revision from the mechanics as well, okay, just at the start. But then we'll go on to electric fields and then magnetic fields. So what we're going to look at today gravitational fields. So the first thing we have to do before we even start is say exactly what a field is. So when I talk about fields, I talk about gravity, magnets, electricity. So does anyone see anything in common with these 3 forces? Gravity force, electric force, magnet force? True, they're all forces. Anything else? Yeah, well, that's only for magnetic. There's the north and the south. Yes, they all kind of have some type of an attraction force. No mass and magnetic force, though. Huh? Yeah, the one thing is that they're invisible forces. You can't see the magnetic force or the gravitational force. You just see what they can do. Okay? Huh? You can only see its effect, its impact, not the actual force itself. So they're invisible. But the other thing is, as you said, they're attractive or they're repulsive. But the main thing about fields, so before we go on to gravitational fields, I'll just say what a field is. A field, so firstly by field is just a mathematical word, firstly, okay? So what is a field? A field is a physical quantity that has a value for each point in space and time. So I'll give you the simplest example I can think of, which would be like in this room. So when you think about this room, and I ask you what's the temperature in this room, you might say something like 22 Celsius, whatever. But then you realize, well, it's not 22 everywhere in the room. Over here, it'll be much warmer where I'm sitting than by the window, for example. So in your head, you're picturing, okay, maybe here by the door, at these places, it's 22. But maybe here by the window, in these places, it could be 20. As an example. So you have this picture in your head at different points in the room, there are different temperatures. Yep. So this is actually a field, because a field gives you a different physical quantity for each point in space and also in time. So for example, as the heaters kept on, then maybe this will change to 23 and this will change to 22 and this will change to 21. Okay? So this is our first simple example of a field. So this is like a temperature field. Okay? Now there are two main types of fields which we're going to have a look at now. So the first one is a scalar field, and then the second one is a vector field. So what do you think this temperature one is? Would you feel like it should be scalar or vector? What do you think? It's scalar because at each point you get a number. But now we'll go on to gravity. Gravity will be a vector field. So if you think about planet Earth, for example, if you're here, you feel a force this way, and if you're here, you feel a bigger force, and if you're over here, you get a smaller force. So this is also a field, because each point gives you a different vector. And what about if you're right here? There's no force. Well, it's complicated. They're all drawn to this point. If you're very far away, there's no force. Okay, so gravity is actually a vector field. So that's our first note then. Okay, so the first thing is we're going to draw it. So if I just go down, if you have a mass m, this is what its field looks like. So here the vectors will be very long. But then when you move further out, they get shorter. They might ask you to draw this in the exam, so this scale that it's getting smaller as it goes out is important. And then if you go further out, it'll be even smaller. So as you get closer, there's more force. And you know the reason for this from semester 1. What's the reason for this? That if you go further out, or if you get closer, there's more or less force. What's the reason for this? Any ideas? No? No, come on, you're not thinking. You remember, Newton said that the force between two masses is g m1 m2 over the distance squared. Yeah, so if the distance gets bigger, this gets smaller then. But what you now can maybe see more is that these are vectors. So this tells you the force at each of these places. So it has a direction. It's always going towards the center. Okay. So this is our first formula. But what I'm going to do is I'm just going to put an arrow here to show that it's a vector. And what I'm going to do is put another vector here. And I know it looks a bit strange, but I'm writing it like this. And what this vector is saying, or maybe someone knows, the unit vector where though? Where's it pointing? Yeah, this just points to the center of the mass. So this is the complete formula, yeah. Yep. Yep. I'll skip an example of this formula because we did this in semester 1, calculating the force between two masses. Okay, so I'm just going to skip that. But I won't skip the next part. So, if I go to this diagram here, in our mind, we can picture that if you're nearer to the center, the force feels stronger. So whenever we have fields, we can talk about the strength of the field. You know, like how concentrated, how strong it is. So if we think about a magnet, it's much stronger when you're close to it than further away, of course. Same goes for gravity as well. So how can we measure how strong the field is? We need some way of measuring it. Okay. Can I scroll down? Do you have this yet? So what we'll do is we'll have our large mass here, and then we'll have our small mass here. And let's calculate the force. It's Gmm over r squared. But we know from Newton's second law that F equals ma. So we can put these together to get ma equals Gmm over r squared. Those m's cancel and we get A equals Gm over r squared. And actually this is a good way to tell us how strong the field is, because if gravity was stronger, what would happen to its acceleration? It would be bigger. So this actually is the way we can tell how strong a gravity field is, by what's its acceleration. So we call it A in Newton, but right now we're going to call it G, which we know from semester 1 still means acceleration, but we've just given it a different name. It's the same meaning, but it just has a different name to get us thinking about the strength. Yeah, which I think maybe I mentioned in semester 1, can't remember for certain. But you're right, this will be called the gravitational field strength. So you can see that for gravitational field strength, it only cares about the distance. Well, and the mass too, but the closer you get, the stronger the field is. Okay. Well, you know what the value is on Earth, don't you? What is it? 9.8. We don't use meters per second squared when we're calling it gravitational field strength. So on the surface of the Earth, it's 9.81, and it's not meters per second squared. We have to change it into kilograms. I can't remember what the G is. I'll have to work it out. Let's work it out on the side. What I'm saying is they don't use meters per second squared. They use the one with newtons, kilograms, and so on in it. Yeah, I'd have to work it out. Well, you know what? It's not important right now. I'll work it out later.
G is meter cubed over second squared kilogram squared.
Yes. I need the one that has newtons in it as well. You know what? I'll just get it later. It's not important right now. So I'll just put this in quotation marks for the moment. I mean, it still is meters per second squared. And it's still 9.81. Okay. Right, so next now. I think what I'm about to do next, you'll find it useful in the last section, atoms, and you might find it useful in chemistry as well, and a bit of revision in semester 1. Can I scroll down? Sorry, yes? Yeah. Okay. potential energy has three different meanings depending if it's positive, zero, or negative. What does it mean if something has positive potential energy? Who can tell me this? What's that? Yeah, but just focus on potential. Try not to mention other things right now. If something has positive potential energy, then it has energy stored inside of it, which means it could do work. Yes? So it can do work. There's energy stored. What about no potential energy? Can't do work, and more importantly, we say that the particle is free. So it has no potential energy means it's free, like it's floating in the middle of space, not near anything. So it's a free particle. But what about negative potential energy? It's possible. What does it mean? Any idea?
They have energy stored, but it can't do work.
Not energy stored, no?
Yeah, it's like a wire for itself. Potential energy more than zero.
No? When potential energy is less than zero, it means that it's trapped, and you must give it energy to free it. So for example, if you look here, when the ball is above the ground, it has energy stored inside it, so it can do work. When the ball is on the ground, it has no potential energy, so it's free. I mean, it's free insofar as you could kick it and it would move, you know. It can't do any work, but it's easy to move. But when the ball is under the ground, it has negative potential energy, which means it's trapped. If you want to free it, you have to give it energy. So this is the meaning of negative potential energy. So write this down if you didn't know this. Okay. That is very important in chemistry too, because have you done ionization? You've done ionization. Have you done energy levels of electrons? All those energy levels of electrons in different orbits, they're all negative numbers. And the reason they're negative is because they're trapped in orbits. If you want to free the electron, if you want to ionize it, you have to give it the exact amount of energy it has in the negative number to make it zero, so it's free. So if something was do you use electron volts, or what unit do you use? Yeah, so if something has minus 1 electron volt in its orbit, it means you have to give it 1 electron volt of energy to cancel it, give it 0 in total, and so it's free. So it's not trapped anymore. Okay, so the negative is important, very important. Right. Couple of potential energy formulas. You remember the one for gravity, that's mgh, yes? But the only problem with this is you have to be near the surface of the Earth. Okay, it doesn't work if you're out in space. What about the potential energy for a spring? Do you remember this one? Not M? A half K, x squared, or delta x squared. A half the spring constant by the extension squared is how much energy is stored in the spring. Okay. And of course you have many other potential energies for many different situations. So the question now is, how can we find the potential energy for any situation? And here's a new formula for you. Potential energy can be found from this formula. Minus integration of the force dx. So this is new. And what I'm going to do is I'm going to show you this formula for how we get this and how we get this. So for example here, on the near the surface of the Earth, what's the force pulling down here? Yeah, minus mg if it's going down. So potential energy equals minus integrate minus mg dx. But mg is a constant. So what happens when you integrate a constant? You get x. So you get here mgx. But here what does x represent? The height. So you get mgh. Now if we look at Hooke's law with the spring, the force this way is minus k delta x. So the potential energy should be minus integrate minus k delta x. Actually, maybe to prevent confusion here, I'll just call it x instead of delta x for the moment, dx. It makes it clear that we need to integrate the x here, and 2 minuses make plus, so that's kx squared over 2. Same formula. So this is very useful. It means you can always find the potential energy if you know what the force is.
Is there such a formula for kinetic energy?
No, kinetic energy is always a half mv squared. There might be something similar, but because kinetic energy is always the same, it's not important, you know. Potential is the one that you'll need to calculate for different forces. Okay, scroll down. So let's go back to Earth, and let's go back to a mass here. So this force we know is gmm over, let's call it x squared, since we'll measure this distance here as x. And since it's going towards the center, I'll put the minus in. Well, no, I won't worry about that just yet. So if I want the potential energy, that should be minus integrate gmm over x squared dx. And you know what, I will put the minus in here, so there's a minus here. I really want to show, I really should have the plus or the minus to show the direction. So the minus being it's going towards the origin instead of away from it. Okay, so that would be gmm integrate x minus 2 dx. So we get gmm x minus 1 over minus 1. So you get minus gmm over x. So you see, this now is the formula for potential energy. Why is it minus though, in potential energy formula? Why does this formula have it minus? Yeah, because it's always trapped, isn't it? I mean, it's minus because it can't be positive. It has to always be minus. Because we, like with the electron, we think of it as being trapped. So if you want to make this free, what are you going to have to make the x? No, but you can't make it negative because it's the distance to the center. So the x here is more like if you want to think about it like this, it's more like an or. So how can I make this particle free? What does it mean to be free? The tangent is 0. So how can I make this 0? No. Well, how? What can I do to make this 0? I can't change the masses.
Divide by 0.
No. If I want to make this 0, I'm going to have to make this OR really big, like going to infinity. So if this OR is extremely large, then what happens to this here? It's extremely small. So it's practically free. Okay? Not quite zero, but practically zero. So, you know, if you're billions and billions and billions of kilometers away, that is practically zero, so you're practically free. But you can possibly maybe still feel some of the force from Earth, even very far away. Okay? But what I'm going to show you now is how come this formula looks so different to the MGH? Well, the reason it looks so different to the MGH formula is because this one is for anywhere in the field. So that's important. I'm going to say it again. This formula is for anywhere in the field, whereas our MGH formula is only near the surface of the Earth. And I'd like to show you that this can be changed into that. So if I scroll down here, so if you're on the surface of the Earth, your or equals big O plus H, where this is big O, and then this distance here is H. So then the potential energy, you can see the formula there, minus GMM over O. But the small or is equal to big O plus H. I'm just writing the same thing again. So if I sub that in, I get minus GMM over big O plus H. Now what I'll do next is I'll divide everything by big O. So I get minus GMM over big O all over 1 plus H over O. Okay, now the H over O, I'll write that as minus H over O. And then what I'll do is I'll say I'll call it X for the moment, equal minus H over O. And the reason I'm doing that is so that I can change this into GMM over big O over 1 minus X. Which is minus GMM over O times 1 over 1 minus X. Now the reason I went to all that trouble just to get 1 over 1 minus X is because from semester 1 maths you might remember there's a formula for 1 over 1 minus X, and it comes from the lesson on long division and the lesson on geometric progressions. 1 over 1 minus X is 1 plus X squared plus X cubed, etc.
Shouldn't be times 1 minus X as part of 1 minus X.
You think this is a mistake here? No, I think this is okay. What I'm doing is like this. This is, what do you think about this?
We divided GMM by R over 1 minus X, that should be 4. So,
no, I think this is okay. It's okay. Now, look here. This distance is very small, and this is very big. So X, will it be very small or very big?
very small.
Very, very small. In fact, it's so small that we're allowed to consider these as being practically zero. If you took out your calculator as an example, and you had a really, really small number, and you square it, it becomes even smaller. And if you cube it, even smaller again. So we can say that this is roughly minus GMM over O 1 plus X, which is roughly minus GMM over O 1 plus X, and we said X was minus H over O. Okay. And actually, if I go back to earlier, so I'll go here, don't worry. Where's my definition gone? Let's not forget that G is given by GM over R squared, and it's roughly 9.81. But anyways, GM over R squared, that's small g. So I can see, let's see if I can use that here. Yeah. Question? No. G big M over R square over R is small g. Now that R is well, which R is that? That's the distance from the center to the well, in that example for 9.81 to the surface, but in general it's the distance between the two centers. So there would be not quite, I couldn't quite use this or. Anyways, let me multiply this out. Minus GMM over R plus GMMH over R squared. Yes. Now, this is where I kind of have to stop because I don't have my list of constants. I don't know off the top of my head what is the mass of the Earth. I don't know what the radius of the Earth is and so on. But you can kind of see from the formula, if I look to the right, you can see I have an M, a small m, and I have a H. So I do want, does your calculator have the mass and radius of the Earth stored on it? Can you check the lid?
Google has it.
Google has everything, yes. Doesn't have it?
Yeah.
Okay. Let me see.
Shall I Google it?
I know, yes. What I need to know is, well, I know what the big G is. I need to know what the mass of the Earth is and the radius of the Earth. So, yes, can someone Google that, please? I want the mass of the Earth and the radius of the Earth.
Why is it?
I want to plug the numbers in, so to get rid of the constant, so we can have a look at numbers.
That's your 5.972 E 24 kilogram. What is
Yeah, 5.9.
72
Yeah.
E 24 kilogram.
Okay. And then the or radius of the Earth.
6,321 kilometers.
6,000.
371 kilometers.
Yeah. So times 10 to the 3. Okay. So can you take out your calculators and tell me what you get for this piece here?
What is our mass?
Oh, sorry. Don't put in the small m. I just mean the G, big M, and or, and that would be multiplied with small m.
Minus 62.5 times 10 to 6.
Minus 62.5. 52, small m. Okay, and then I need the next one, please.
It's 10 to the power 6.
Oh, 10 to the power of 6.
Yeah,
Are we sure about these numbers then? Well, the 10 to the 6 is 10 to the 6, but that's huge. Oh, 10 to the minus 6?
No. Minus 62.5
Positive 6. 100% sure?
Yeah.
Okay, and give me the next one then. Plus, and there's a small m there too.
Instead of positive 6.
So yes, I know. Positive 6. Small m plus
Minus 9.81 G, basically. MG.
yeah, minus 9.81, which basically and there's an m here, and then the h is still here. So you can see this is roughly this really big number minus mgh. So something went a tad wrong because I was expecting, oh no, actually that's okay. Well, that's okay. I'm disappointed by the, oh wait, it's not minus, it's plus. Great.
No, it is minus.
Oh, there's plus here.
Yeah, but it's minus 9.81.
But how did you get minus if all these numbers are positive?
Oh yeah, it's like,
Yes.
I forgot to take out the minus.
Okay, so we're good. So we got potential energy equals some big number plus mgh. So we almost have it, but the problem is we have this really, really big number in the formula. But this is the weird thing about potential energy. And you'll see this more at university, especially when you do dynamics. But the weird thing about potential energy is it's not important, and it doesn't change the situation if you add or subtract a constant to the formula. And the reason for this, I can give you two examples for this. If you think about voltage, okay, remember that voltage tells you the voltage between 2 points, yes? You put your voltmeter around 2 points. So voltage only can tell you the difference between 2 points. And actually, it's the same thing with potential energy. What you're really saying with the mgh formula is the difference in potential energy between two heights. It's not really the potential energy, because you now know that the potential energy is not just mgh. You have to also consider how far you are from the center of the Earth. So this mgh formula is good, and it works when we're only talking about the surface of the Earth, and we pretend that the ground is the end of the story, but of course it's not. So the mgh tells us the energy at different heights, but it doesn't really tell us, you know, the energy if we were below ground, if we were very far away. So there is more to the formula. But that big number, I can actually cancel it. And the reason I can cancel it is it doesn't actually change things. I'll give you a very, very small explanation why, mathematically. You know that potential energy is minus integrate f dx. So that means the derivative of potential energy, that equals minus f. Yes? So that means f equals derivative with a minus of potential energy. Now what if I add a constant to potential energy? Potential energy plus constant. Is that the same or different f? Same or different f?
Oh, okay.
Yeah, it's the same force, isn't it?
Yeah.
So the way we approach this was, if you have a force, then you can find potential energy. I'm saying, think about it backwards for a moment. If I give you the potential energy, then you can find the force. But notice, if I give you the same potential energy plus a constant, you still get the same force. In other words, you can ignore constants in the potential energy formula. Think about all the potential energy formulas you know. MGH, does that have a plus constant in it? No. A half K delta X squared, does that have a plus constant in it? No. So all plus constants can be ignored in the potential energy formula. So then we end up with potential energy near the surface equals MGH. So although it looks very, very different to the formula I had earlier, where's it gone? Here. It looks quite different to it. It actually comes from that formula as well. Alright, let's see how we're doing. Yes, I just want to do one example. So a lot of the material in this lesson was advanced, and it needed to be done because the stuff later in the chapter will use lots of ideas from this. But the actual questions in the exam for this topic are not so difficult. So for example, I'll do something like, I'll just do the first one. So you have your Earth here, and you have your satellite here. So this is Earth, this is satellite. The mass here is 5.983 times 10 to the 24, and the mass here we don't know. And the radius of the Earth is 6378 kilometers. Oh, and the distance here is 200 kilometers. So my question then is, what's the time it takes to go around the Earth once? So it's like what we did in semester 1, it's more a revision than anything else. We'll work it out. So we have F equals GMM over R squared, but F equals MA. So you get MA equals GMM over R squared. And you realize now that the small m is not important. So we get A equals GM over R squared. But you also know that's moving in a circle, so you can use the formula F equals, what's it, M omega squared R. And you also have F equals MA, so you get then MA equals M omega squared R. Yes, we're getting there. So A equals omega squared R as well. So what you've done is you've found two formulas for A, and we can now equate these. So you get GM over R squared equals omega squared R. So you get omega squared equals GM over R cubed. So omega is square root GM over R cubed. But then you need to remember that omega equals 2 pi over t. So therefore, t equals 2 pi over omega. So what you've done now is you've gotten the formula to work out the time. So we just plug in the numbers. 2 pi square root 6378000 plus 200,000 cubed all over 6.67 times 10 to the minus 11 times the mass of the Earth, which is 5.983 times 10 to the 24. So can you just hit that in on the calculator, and we'll just leave that as our example. In total for everything?
Yeah.
5 point,
5.30 times 10 to the power
5.30 times 10 to the 3 seconds. Let me just get this in, divide that by 60. Is this not it?
88.
88. What answer did you get?
This curve.
Wait, which one? The one I just had?
That's 5.30.
Okay. 5.306 seconds. Roughly 88 minutes.
So, times relation.
Yeah. No, it's the 200 kilometers is about the same orbit as the International Space Station. There's 200.
I guess what 200?
It's 200 kilometers in the question, which
okay. Question.
yes, which is about the same orbit as the International Space Station, which I think takes 90 minutes to go around this. I'm not too impressed. So for the exam, you can really see that it's really just stuff from semester 1 for this topic. But that doesn't mean all the theory I did is unimportant. It is very important for the rest of the chapter when we start talking about magnets and electric fields. And then when we go on to atoms, when we talk about electrons in orbit as well. Okay? Let me give you these. Let's see, we have 2 classes tomorrow, isn't it? And then
2 classes after tomorrow.
2 classes on Thursday, then 1 on Friday.
No. Today 1, tomorrow 2. Today
1, 2, 2.
0.
So Thursday, again, Thursday for 1 hour will be the lab then.
Maybe a bit more. This one is a very
Do you feel like you need more than this time?
Yeah.
Give me your opinion.
Yeah, sure.
Yes? Okay, so then Thursday,
1 hour 10 minutes.
something like this, yes. Well, we'll just see how it goes. As soon as we finish whatever it is I need to do on Thursday, then we'll go straight into the lab, okay? Right, so have these done for tomorrow. They're really good revision as well from semester 1 when you did the circular motion and Newton's law of gravity.